Thanks for tuning in for the unit test review for Unit 4. I was sick earlier this week, so that's why my voice sounds awesome. So this first set of questions is with no calculator, as denoted here. I expect you to be able to knock these out without a calculator, especially the first one, because I can see pretty quickly that this is a stretch factor of 1. And recall that that's going to look similar to a 1 over x function that has pretty simple set of points to recall. In the top right region, you have 1, 1. You also have 2, 1/2, and 1/2, 2. And then down here in the bottom left quadrant, you got some similar action of -1, -1, and those other options of like -2, -1/2, -1/2, -2, so on and so forth. So this one I see is going to be similar to that because it's a stretch factor of 1. You'll take all these points and move them to the right 4 and then up 3. So quick sketch of this will be here in a moment. So hopefully you got these points here. This is 5 of the 6 that I sketched out. I'll leave it up to you to figure out what that 6th point is, which is right there. For problem 2, I see that the stretch factor here is 4. And why does that change things up? Well, it's pretty much saying that instead of being over 1, up 1 to get the most like further out point on your lines, you're going to have to go over 4, up 1, and also up 1 over 4. So we'll see this in a second. But at a quick glance, this is going to have a vertical upness of 2. I see we're subtracting 4 over x, which means that we're going to have to flip this over the new set of axes or asymptotes that we're going to create. And I see that this is also, again, a stretch factor of 4. So since this is review, I'm just going to pause the video and sketch these out, and then hopefully they make sense how I got them. So here you go. Again, this went up 2 units. Your new horizontal asymptote is y equals 2. It's flipped over, so it's not normally top right and bottom left. It's switched. And notice how I have these points, which are respectively, you can kind of think of this as the slope of like -4, because I went 4 units up and then back 1. And then I also did something similar of 4 units in this direction and then up 1. So you can kind of think of that as a way to get your points respectively, that it's 4 units away and then 1 unit down, 4 units away, 1 unit down to get those points respectively, which are mapped out in this table here. Hope that helps. So this shouldn't be too bad, pretty basic. We see now that we have more action in the denominator. I would follow through with the steps that I'm going to give you here. This is personally the set of steps I go through, and this is, I'm pretty sure, the same set of steps that integrated went with as well, of getting your vertical asymptote first and the horizontal. And then what else do? We check for our intercepts. And then I think that's it. So recall that your vertical asymptotes are big on this part of the denominator. So if you set each of these factors equal to 0 and solve them, you'll see that you end up with 2 vertical asymptotes. One is where x equals 2, and another where x is -5. We'll graph all of this once we have all this information down. So the horizontal asymptote, I see that my top degree, and maybe make a note of this, that the top degree is like x to the 0 power, because think of this as just a constant. And then down here, this would eventually produce x times x, which means that it's x squared. And so in this case, the bottom degree is greater than the top, which means that you have a horizontal asymptote at y equals 0. Capiche? And then the intercepts. Luckily, this is going to be pretty an easy one because the x-intercepts will occur when y is 0. But really, to solve that, you're just setting the top equal to 0 and solving that. Well, let me ask you, can 1 ever equal 0? So in this case, there are no x-intercepts. However, for the y-intercept, we're going to have one, because how do we get that? You plug in donde x equals 0 and then solve for what's left over. So if you do that pretty quickly, you get 1 up top, same as it ever was, -2 in the one factor or binomial, now monomial, and then 5 down here. So this is saying that you're going to end up with a y-intercept of -1/10. So I'll sketch out some of these lines and then we'll take it from there in a moment. All right, so right now you're probably saying that's as good as it can get. I only know about this one point, the y-intercept, and it's a measly -1/10. So how do I know what's happening here, even in here, and also out here? Well, you know that to the right of this vertical asymptote, you hit this point here where x is 3. So you could do a quick f of 3, which is going to produce this. 3 minus 2, 3 plus 5 in the other. So this is really going to be 1 over 1 times 8, which is an eighth. And that helps. Why? Because this means that you should only have action in this top right corner, which means that towards the left side, on the other left, the other side of this asymptote, think about this. This line on the right's going up, so this should be going down accordingly, like so. And that does help quite a bit. So to try and figure out what's going to happen in the rest of here, you could plug in points, but I think you're better than that, because you can just think like what's going to happen here. This is going to tell you the corner, and then that will kind of help you dictate where this line is going to have to continue in the middle. So what could you do? If this is where x is -5, you could plug in -6. Do that. Gets you 1 over -8 times -1. So this is going to be 1/8. And that helps because, again, we know it's going to be in the top left quadrant. We're not really a quadrant. We're not really talking quarters at this point, but this top left pocket. And so that helps because this line should be like so. Meaning this has to go up. So that means this has to go down. So that means that this will eventually have to kind of corner around, go down. If you're not convinced that that works, check Desmos. But if you really think about it, I only had to plug in and get 3 points. The y-intercept, a point to the right of this vertical asymptote, point to the left of this vertical asymptote. And then I just kind of understood the pattern that, like, well, if this goes up here, on the flip side, this should go down. I hope that makes sense. I'll give you a moment to try 4 because I think that one's pretty simple when you simplify it all out. So if you simplified this correctly, you should be able to notice x squared minus 2x minus 8 can be factored to this. You can then cancel an x minus 4. And you really, all you have to do is graph this, with the exception of now there's going to be a hole at the root of this, which would have been 4. And if you map this out where x is 4, it's going to produce 1/6. So all of these features should be enough for you to graph that out on your own. Okay, sound good? I think that was the that was it for the oh no, there's more non-calculator, but I hope that these first 4 were helpful. We'll see the rest in a moment. All right, let's do this. Well, every equation we can write for these asymptotes, at a glance, the horizontal asymptote's pretty simple because we see the top degree equals the bottom. And so that means that our leading coefficients are going to be that horizontal asymptote. So this is going to occur at 3 over 1, which is just y equals 3. Horizontal asymptote's going to occur based on the denominator. So set that equal to 0, solve it. You're then going to say x is 4. And so there's no slant asymptote because the slant asymptote only occurs when the top exceeds the bottom degree. So in this case, just say there's none. for now. Capiche? Simple. G of x. This can be factored. That's one of the first things you should do, because if things cancel, it makes it a lot easier to work with, right? Doesn't it? And does this even factor out to that? No, I don't think it does. So interesting. We're back to the drawing board, because you could try and try, but this is not going to foil out nicely or factor out nicely. So I'll just stick to the boring routine. Horizontal asymptote. We see that the top degree is greater than the bottom. So that actually means that there's going to be a slant asymptote. And that implies that there's going to be no horizontal asymptote. But there's definitely a vertical asymptote when x is 3. So how can we get the slant asymptote? Well, we know that we could do long division for this. And whatever your quotient is, that's going to be the slant asymptote. But luckily, our divisor is an x minus or x plus some number. So I'm just going to use synthetic to do this. I hope you don't mind. And if you aren't so hot with synthetic, I think I talked about it in a previous Ready, Set, Go video. So try to reference that if you can. So 1 leading coefficient for x squared drops like it's hot. -2 is there, and then 3. So I hope you understand where these are coming from. Again, I got this 3 because that's the root of x minus 3. So 3 times 1, that's 3. -2 plus 3 is 1. 3 times 1 is 3. And so what does this really mean? This is saying that you're really just graphing 6, your remainder, over x minus 3, but you're shifting this in accordance to this, which has a constant of 1 and then one form of x. So in this case, your slant asymptote is y equals x plus 1. If you're not convinced, check it, graph it, but you'll eventually see that there's going to be a linear line that's kind of not drawn, but the function is working around it respectively. This is a pretty super quick sketch of this, but I think this kind of, hey, you know what? I might even do the rest of the sketch, because you would have these two asymptotes. And then what else could you say? You could say that you end up with a positive y-intercept, right? What's the y-intercept? It's going to be 0. Let me actually, yeah. No, sorry. Let me just think this out real quick. So if you have a y-intercept that occurs when x is 0, and that means it's going to be -1. So interestingly enough, you would have a graph that looks like this. It'll like curve up, come down from here, curve up, and then tries to like form with the linear line. If you're not convinced, try it out. And then this will probably do something similar up here. Again, try it out if you're not convinced, but I think that's roughly how it is. This is like not a very good sketch at all, but you know, you see that you have the vertical asymptote, slant asymptote, and there's no horizontal. So I hope that helps. I'm going to give you a minute to try 7. So you're asked to give all these features here. I hope that this is more than enough. Again, x-intercepts, you get that from setting the top set of factors equal to 0 and solving that. Y-intercept occurs when x is 0. So again, just plug in where x equals 0 everywhere. That's a key thing. The bottom degree is greater than the top. So it's just to kind of think of it as like 1 over x. That's a pretty typical like baseline to fall back on if you forget those rules, because this has a horizontal asymptote of y equals 0. Vertical asymptotes are based off of the bottom factors when they're set equal to 0. And these are, you know, linear lines. And then the domain is all real numbers with the exception that x can't equal 1 or -4, because if x equals 1 or -4, this whole function becomes undefined, and that's no bueno. Hope that this was helpful. And so now back to the calculator portion. This is, I think, like I don't know. These are pretty simple if you know how to factor. So just try to factor each bit as much as you can. I look at the top of this and I see 2, common factor of 2x and 4. So I take 2 out. Down here, I can rewrite this as x plus 3, x plus 4. Is that really it? Can't do anything else, I don't think. Factor and simplify, I think that's it. Nothing cancels, and I guess that's a good thing. Upon further inspection, yeah, I think that's it. Wow, fascinating. Nothing canceled. Difference of squares up here, which again means that it's going to be x plus or minus the square root of this constant. And that'll give you those 2 binomials, Okay, so this is x plus 3, x minus 3. Down here, factors of negative 18 that add up to negative 3. So it's going to have to be negative 6 and 3. So cancel them. And then all you're left with is x minus 3 over x minus 6. Boom. Not too bad, right? Addition and subtraction. Again, you need common denominators. You need them like you need water in the desert. You need them like I need to get a new voice. If you have any for the low, let me know. But how I approach this, since I'm adding, I'll make a note on the side sometimes of like what's the ideal common denominator going to consist of. And I see one as x plus 2 and the other is x minus 2. So to me, this is saying that if it has x minus 2, what should it multiply by to match this? Hopefully you're saying x plus 2. And then over here, this is missing x minus 2. And if you distribute 4 in, it gives you 4x minus 8. And now you're adding on 3x plus 6. And again, this is now all over the same denominator, which is going to be a nice little difference of squares, just factored out. If we combine like terms, 4x, 3x gets you 7x, negative 8 plus 6, negative 2. And then that's about as good as it can get. Cool. Same song and dance here. Just be careful because now you're subtracting whatever you end up with here. So at a quick glance, you have a denominator of x minus 2. And in the other denominator, it's x plus 3. So la-di-da, make sure this gets x plus 3. And this is missing x minus 2, even though there's a numerator of x minus 2 up here. You wouldn't want to cancel these and say that they're gone. So don't do that. That's no good. Bad time. You can FOIL this out, and that gets x squared plus 9x plus 18. And remember, you're subtracting all of this. X squared minus 4x plus 4. And now it's all over this one fraction. This is going to be such a long video. If you are watching all of this, gosh, you're just amazing. That's incredible. X squareds can cancel. Be careful now. You're subtracting negative 4x. So 9x plus 4x gets you 13x. 18 minus 4 is 14. Oh, I'm getting hungry. I think I have guac and chips. I'll have that as an app. I think there's some salad left over too. Should be a good time. All right, multiplication and division are super easy. So recall, if it's division, big alert that you're going to really just have to flip this fraction and then multiply. So really, core of this is just that you're now multiplying that first fraction with x plus 4 over x minus 1. And do you see anything that's going to make our life easier? I do. X minus 1 can cancel here and here. Because again, you're multiplying straight across. So you could even go so far as to like make this all one fraction as soon as you flip the second fraction. And boom, you're only left with x plus 4 over x plus 2. Capiche? I'm going to give you a moment to try this one. Factor out everything and then cancel what you can. Kind of a boring problem. You factor out everything that you can. And the only thing that cancels is this whack little x plus 1. So this is your final answer. It's as good as it can get. There's nothing else you can take care of and factor out. And even at a quick glance, I think all of my factoring's good. I'd say the one thing that I almost made a blooper on was right here, saying that this was going to be x minus 2, x minus 3. But then that would make this a positive 6. Notice it's negative 6. Yeah, so there you go. This one's so light. I mean, you could do all of the simplifying, or you could just look at the denominator and say, oh, well, if this was negative 6 for x, that's going to go undefined, and that would make it extraneous. That's a pretty simple one. So just set the denominator. I mean, like, actually, you know what? Like, don't do it, but do it, because this is like hinting that this is going to make it extraneous. Because even if you factor out the top, like so, and cancel x plus 6 respectively, claiming that it's gonna like, I mean, like it doesn't really cancel, but if you had to set this all equal to 0, that would only be based off of up here being set equal to 0, and you would get x is negative 6 and 4. But when you plug it back in, it's going to make it undefined because you have negative 6 going down here with 6, and that goes undefined. So there you go. Super chill, super easy. Solve for A. Your ideal common denominator has two things. What are they? Definitely an A minus 2 and definitely a 3. So this is light work. Make sure 3 goes here to the first fraction. Also here to the second fraction. And then this is missing that pivotal A minus 2. Okay, so distribute 3. It gets you 9A minus 12. You're now saying this is equal to 3 times 3, which is 9. And then distribute 2A. So now add on 2A squared minus 4A. And again, I said this in class the other day. You can be lazy with confidence if you know that you did this right. But if you feel as if it would just help your mental checklist, just like, oh, yeah, everything does have 3 and A minus 2. If you really want to write that out under all these fractions, by all means. But eventually you just focusing in on the numerators, which are just going to say that you have 9A minus 12 equals 9 plus 2A squared minus 4A. So you have an A squared term here, so you're going to be better off setting all of the terms to one side and then solving for 0. And I'll even make a note of that real quick. So let me switch tools. Is that big enough for you? Do you get that? You have an A squared term in there, so you're going to have to take each term to the other side or, to the same side. So there's an A squared term, move all terms to the same side and then factor respectively. Okay. So I think the easiest thing to do is to move the left side terms to the right. So again, opposites attract. This should all cancel now, go to 0. Clean this up a little bit. Have 2A squared minus 13A plus 21. Well, this one's going to be a little challenging. Check us out. Totally capable, though. All right. Well, you could think out factors of 42 that add up to negative 13. Let me actually pause the video and make sure that this is going right so far. So yeah, it does work. -6 and -7 are going to work just fine. So how I approach this, I know 2 is prime. I could, get crazy and just say, well, it's going to be 2a here, and there's going to be an a term here, and you can play with the numbers of 21. But I'm going to play it light and just say that I'm going to rewrite the middle like so. And then this is factoring by grouping. You remember that, right? Factor first 2 terms. If there's anything common, take it out. And if this is done correctly, you should see another a minus 3 over here, which would make -7 have to pop out here, respectively. And then take it all to, there's one binomial where it's the 2 greatest common factors you plucked out. And then just one version of that binomial that you solved twice. And remember, this is all set equal to 0. So if you solve these two, set them equal to 0, solve them, you're going to claim that a could be 7/2 or 3. But recall, you want to check for if there's anything that's extraneous. And at a quick glance, I think we're off the hook. I think these are all going to boil out just fine. Reason being is that if you plug in 7/2 or 3 to either denominator where there's a variable, it doesn't go undefined. So that's a key thing. So you got 2 answers here. I hope that this was helpful. There are some other questions that deal with kind of like the classwork we did of 60 over x and making those fractions respectively. There's also one, I think, in the homework where it was like 15 over x plus 15 over 2x equals 1. So we'll practice problems like that when I see you, or you can shoot me an email and I will send you some sooner. But I hope that this was helpful. If you have any questions, reach out, pray for my voice, take care, brush your hair, get a good night's sleep, go drink a glass of water. Goodbye.